November 11th, 1940. The night sky over Taranto harbor is torn apart by flares and anti-aircraft fire. At the center of the chaos sits the Italian battleship Conte di Cavour. She is 29,000 tons of sovereign territory, a floating fortress designed to withstand the heaviest shellfire the Mediterranean can throw at her. But at 23:15, a single slow-moving biplane changes the equation. It releases an 18-inch Mark 12 aerial torpedo into the black water. The weapon has been adapted for shallow water work so it can enter without a deep dive and still stabilize into a running depth. The weapon is 18 inches in diameter. It runs true. It does not strike the heavy side armor belt. It dives deep toward the turn of the bilge. The resulting explosion is not just a structural failure, it is the defeat of a specific engineering philosophy. The Cavour was protected by one of the most advanced and controversial underwater defense systems of the 20th century. It was known as the Pugliese cylinder. Most navies protected their battleships with layers of air and liquid-filled compartments designed to slow down a blast. The Italians took a different path. They built the Pugliese system. A corner of the hull was filled with liquid, water or oil, and inside that liquid volume sat a hollow cylinder meant to collapse under shock. The concept was not to prevent flooding. The concept was to consume the blast before it reached the inner bulkhead. The physics concept was elegant. If a torpedo struck the outer hull, the energy of the explosion would crush the outer drum. The force would then hammer against the inner water-filled cylinder. Because water is incompressible, the inner cylinder would be forced to collapse inward, absorbing the shock wave like a giant hydraulic crumple zone. The system relied on the geometry of the impact. It assumed the enemy warhead would strike the side of the ship where the cylinder was widest. The British torpedo did not cooperate with the geometry. Underwater protection is built out of depth, and depth is exactly what runs out in confined water and fine hull lines. The detonation happens where the scheme is least able to unfold, beneath the forward section under B turret. The blast bypassed the absorption mechanics entirely. It opened a breach on the order of 12 meters by 8 meters, roughly 39 by 26 feet, under B turret. The shockwave did not meet a crumple zone. It met the rigid structural steel of the magazines and the hull bottom. The sea rushed in. The flooding was immediate and catastrophic. This is the moment where a damage control problem transforms into a salvage crisis. The Cavour began to list. Her captain assessed the intake rate and realized the pumps could not win. He made the only logical recommendation available. He asked permission to tow the ship immediately to a nearby sandbank. The water there was only 40 feet deep. If he grounded her there, the main deck would remain dry. The machinery would be saved. The recovery would be a matter of weeks. But in a rigid command structure, physics often takes a backseat to protocol. The admiral in charge, Bruno Brivonesi, hesitated. He believed the watertight bulkheads would hold. He believed the list could be corrected by counterflooding. He denied the request to ground the ship. For critical minutes, the Cavour drifted in the darkness, taking on thousands of tons of water. By the time the order was finally given to beach her, it was too late. The battleship drifted past the 40-foot shoal. She settled into the mud in deeper water, finding bottom at 56 feet. The difference of 16 feet was fatal. The ship did not just ground. She sank. The main deck disappeared beneath the surface. The bow vanished. Only the superstructure and the rear turrets remained visible above the waterline. The admiral had gambled on stability and lost. The Conte di Cavour was no longer a warship. She was a steel island embedded in the bottom of the harbor. The problem was no longer about keeping her afloat. It was about breaking the grip of the sea floor. The Italian Navy faced a problem that could not be solved by gunfire or seamanship. The Conte di Cavour was resting at a depth of 56 feet. Her bow was buried deep in the sediment of the Mar Grande. The quarterdeck was awash. She was a 29,000-ton steel monument to the raid. But the weight of the steel was not the primary enemy. The enemy was the seabed itself. When a ship sinks onto a hard surface like rock or compacted sand, she merely rests there. The salvage engineer calculates the displacement of the vessel and applies a lifting force slightly greater than that weight, but the harbor floor at Taranto is not rock. It is a thick, cohesive clay mud. When a heavy object strikes this material, it does not just sit on top, it penetrates. The hull of the battleship had driven itself deep into the substrate, creating a seal that was nearly airtight. This introduces a lethal variable known in salvage engineering as breakout force. To lift the ship, you cannot simply overcome gravity. You must overcome the adhesion between the steel hull and the clay. The mud creates a vacuum effect. As you try to lift the hull, the water cannot rush in fast enough to fill the void underneath. The suction holds the ship down with a force that can be double or triple the actual weight of the vessel. If you apply too much tension to the lifting cables before this suction is broken, the cables will snap or the hull girders will buckle. The ocean floor does not negotiate. It has to be tricked. The Regia Marina realized immediately that this operation was beyond their standard damage control capabilities. The port was already choked with damaged destroyers and cruisers. They needed a specialist. In a decision that mixed desperation with irony, they reached out to the private sector. They awarded the salvage contract to the Tripcovich Company of Trieste. This was a civilian firm specializing in heavy commercial salvage. They brought with them floating cranes, pontoons, and a different mindset. But they also needed someone who understood the internal anatomy of the beast. The Navy made a call to a ghost. General Umberto Pugliese was the most brilliant naval architect of his generation. He was the father of the underwater defense system that had just failed. 2 years earlier, he had been forced out of the service and into isolation by the racial laws of 1938. Now, with his masterpiece lying broken in the mud, the Navy ordered him back into uniform. He was not given his rank back. He was brought in as a consultant. He accepted the job. He was the only man who knew the load paths of the Cavour intimately enough to advise on how to lift her without breaking her back. The team faced a geometry trap. They could not simply patch the hole and pump the ship dry because the hole was buried in the mud. They could not lift the ship to get to the hole because the mud would not let go. It was a closed loop of impossibility. Pugliese and the Tripcovich engineers devised a strategy of subtraction. If they could not increase the lifting force, they had to decrease the holding weight. They would have to strip the battleship down to a skeleton. Every ton of steel removed from the topside was one less ton the mud could use against them. The plan required turning the salvage site into a demolition zone. The pride of the fleet would have to be dismantled piece by piece before she could ever rise again. The salvage plan required a trade-off that pained every naval officer who watched it. To give the Conte di Cavour enough buoyancy to break free from the mud, the engineers had to destroy her combat value. The ship was simply too heavy for the available lifting pontoons. The solution was radical weight reduction. This meant stripping the battleship down to the waterline. It was a process of reverse construction where the most powerful weapons in the Italian arsenal were treated as scrap metal to be discarded. The engineers targeted the high structures first. The massive forward funnel was cut away with torches and removed. The command tower was dismantled. But the real weight lay in the main battery. The Cavour carried 10 heavy guns each with a bore of 12.6 inches. These rifles and their armored turrets weighed hundreds of tons. Removing them was not just a matter of lifting capacity, it was a delicate exercise in stability physics. Every floating vessel is governed by a geometric relationship known as metacentric height. It is the vertical distance between the center of gravity which pushes down and the center of buoyancy which pushes up. Think of the ship like a pendulum or a weighted roly-poly toy. If the center of gravity is too high, the pendulum is top-heavy. The ship becomes tender. It rolls easily, and if pushed too far, it will not return to upright. It will capsize. If the center of gravity is low, the pendulum is stable and resists rolling. By removing the massive guns and the heavy steel of the superstructure from the top of the ship, the salvage team was deliberately lowering the center of gravity. This lowered the center of mass relative to the center of buoyancy, increasing the metacentric height. This made the ship incredibly stiff and stable in theory. It ensured that when they eventually tried to lift her, she would not roll over and kill the salvage crew. But this massive alteration of mass also altered the stress loads on the hull frame. This weight removal was conducted under a shadow of paranoia. Naval intelligence and the engineering team were debating a fringe technical theory about the weapon that sank her. The British torpedo had exploded deep under the hull. Some Italian experts believed the warhead had been equipped with a magnetic pistol. A magnetic pistol detonates the charge not on contact with the side armor, but when it senses the magnetic field of the keel. If this was true, the explosion had not just punched a hole, it might have snapped the ship's spine. The magnetic theory terrified the salvage team. If the keel was broken, the ship was no longer a rigid beam. It was two separate sections held together by deck plating. If they removed too much weight from the bow or the stern, they risked unbalancing the load. The ship could hog or sag, causing the weakened keel to snap completely. The engineers had to calculate the weight removal sequence with extreme precision to ensure the hull remained neutral. They were lightening a structure that might already be broken. Work crews swarmed the listing deck. They burned through steel and hoisted the heavy artillery away. The secondary turrets were pulled out. The masts came down. By the time the demolition phase was finished, the Conte di Cavour looked less like a battleship and more like a flat industrial barge. She was lighter. Her center of gravity was low. But inside the hull, 20,000 tons of water were still waiting. The static phase was over. The dynamic phase was about to begin. The salvage team had successfully stripped the Conte di Cavour of her guns and her superstructure. They had lowered her center of gravity and reduced the grip of the mud. But a new and invisible enemy waited inside the hull. The battleship was essentially a flooded labyrinth. The lower decks were submerged under 20,000 tons of seawater. This massive volume of liquid was the direct consequence of the delay in the grounding order. Because Admiral Brivonesi had waited too long to beach the ship, the flooding had not been contained to the bow. It had spread through the ventilation trunks and cable runs until it compromised almost every compartment. This water presented a deadly problem known in naval architecture as the free surface effect. It is the single most dangerous phenomenon in salvage operations involving pumped compartments. To understand the danger, you must visualize how water behaves inside a container. When a compartment is completely full, the water is pressed tight against the ceiling. It cannot move. It acts exactly like a solid block of concrete. It adds weight, but it does not shift. It is predictable. However, as soon as the salvage pumps begin to run, the situation changes. As the water level drops even by a few inches, a gap opens up between the surface of the water and the deckhead. The water is no longer a solid block. It is now free to move. If the ship rolls even 1 degree to the port side, all that water rushes across the compartment to the port side. The weight shifts exactly when you do not want it to. It chases the roll. This shifting weight creates a geometric anomaly. It causes a virtual rise in the center of gravity. In the previous phase, the engineers had worked tirelessly to lower the center of gravity by cutting off the guns. Now the free surface effect was undoing that work. It was pushing the center of gravity back up, effectively making the ship top-heavy from the inside out. If the pumps lowered the water level in too many compartments simultaneously, the Cavour would lose her stability. She would not just float, she would capsize. The engineers calculated that the internal water had a surface area of over 1,000 square feet. This meant the potential for weight transfer was massive. The ship was entering a state of negative stability, where the very act of trying to save her increased the probability of losing her. The pumps had to be managed like a musical instrument. They could not simply drain the ship. They had to drain specific tanks in a specific sequence to keep the free surface area to a minimum. The entire operation balanced on this hydraulic knife edge. The team had lightened the ship, and they understood the fluid dynamics. But none of the math mattered if they could not stop the ocean from getting back in. The pumps could handle the internal volume, but they could not fight the sea itself. The 20,000 tons of water had entered through a massive breach in the hull, and until that breach was closed, the Conte di Cavour was just an open bucket resting on the bottom. The time had come to address the wound itself. The salvage operation had now consumed 8 months of labor. It was July 1941. The Conte di Cavour had been lightened, and the physics of her internal flooding were understood. But the entire project now depended on a single critical interface. The pumps could move thousands of tons of water per hour, but they could not compete with the ocean if the hull breach remained open. The hole under turret 2 was 40 feet long and 26 feet wide. It was a jagged wound located on the curved section of the bilge buried in the mud. Standard damage control plugs were useless against a gap of this magnitude. The engineers had to deploy a technique known as cofferdamming. In a shipyard, a cofferdam is a dry chamber built to exclude water. In salvage, it is a massive temporary patch that functions like a parasitic hull. The Tripcovich team constructed a giant wooden and steel shield shaped to match the curvature of the battleship. The engineering principle relied on the very force that was trying to sink the ship. The Cofferdam was lowered into the blind darkness of the harbor floor. Divers had to guide it into position by touch alone. They were working in water with zero visibility, suspended in a mixture of silt and fuel oil. Once the structure was aligned over the hole, they sealed the edges against the steel skin of the battleship. Then the pumps began to remove the water from the small space between the patch and the hull. As the pressure inside this space dropped, the immense weight of the outside ocean pressed the patch tighter against the ship. The sea itself was being used to hold the bandage in place. With the breach sealed, the main dewatering phase began. The pumps roared to life, removing water from the forward compartments. The engineers watched the inclinometers with obsession. They were looking for the moment of breakout. This was the second where the buoyancy of the ship finally exceeded the suction of the clay bottom. It was a violent transition. The hull groaned as the steel girders flexed. The mud refused to let go until the lifting force was overwhelming. Then, with a sudden shudder, the Conte di Cavour tore herself free from the bottom. The bow rose. For the first time in nearly a year, the forecastle broke the surface. The water poured off the rusted teak decks. The ship was listing and covered in marine growth, but she was floating. The salvage master had won the argument against the seabed. But the Cavour was not yet safe. She was a fragile shell relying on a temporary wooden patch to keep the Mediterranean out. She could not be towed to a distant shipyard in this condition. The solution was the largest piece of auxiliary equipment in the Italian inventory. It was known as Floating Dry Dock GO-12. This massive structure was capable of lifting 60,000 tons. It had been positioned nearby to receive the patient. Tugboats latched onto the resurrected battleship and guided her slowly toward the submerged dock. The Cavour was maneuvered over the blocks, and the dock began to pump its own ballast tanks. As the dock rose, it lifted the battleship completely out of the water. The mud-encrusted hull was finally dry. The salvage was a technical triumph. The ship had been returned to the surface. Now the Navy had to decide what to do with her. The raising of the Conte di Cavour was celebrated as a miracle of Italian engineering. In July 1941, the battleship was floating on her own bottom. The mud of Taranto had been defeated. The Tripcovich salvage team had executed a textbook operation under the nose of the enemy. But in the cold calculus of war, a salvage success is only valuable if it results in a combat asset. The Cavour had consumed thousands of man-hours and millions of lyre to reach the surface. Now she demanded even more to become a warship again. The ship was too damaged to be repaired in the active war zone of southern Italy. She had to be moved to the safety of the northern Adriatic. A fleet of tugs hauled the crippled giant all the way to Trieste. It was a long, melancholy procession. The battleship was a hollow shell. She had no main guns. Her funnel was gone. Her electrical systems were corroded by salt water. She was a hull number in search of a mission. Once in Trieste, the Regia Marina did not just plan to repair her, they planned to modernize her. They designed new anti-aircraft batteries and updated fire control systems. They began the slow, laborious process of cleaning the interior and reinstalling the heavy machinery. But the timeline of the shipyard could not keep pace with the timeline of the war. 1942 came and went. The steel that should have gone into new tanks or destroyers was poured into the ghost of the Cavour. She became a strategic black hole, absorbing resources without offering any projection of power. By September 1943, the geopolitical landscape shifted violently. Italy signed an armistice with the Allies. The German Wehrmacht immediately moved to occupy key Italian ports. The Conte di Cavour was still sitting in the dock at Trieste, far from operational status. Her crew could not take her to sea. She was captured where she sat. The Germans had no interest in finishing the repairs. They stripped her of anything useful and left her to rot. The final indignity came in February 1945. Allied bombers found the harbor at Trieste. They did not see a derelict wreck. They saw a battleship. They attacked. A bomb struck the ship, and for the second time in 5 years, the Conte di Cavour took on water and capsized. She rolled over and settled into the mud, her keel pointing at the sky. She remained there until the war ended. In 1946, the new Italian government made the final decision. She was refloated one last time, not to be saved, but to be cut apart for scrap. The legacy of the Conte di Cavour is defined by a deep and bitter irony. She was the vessel that proved the failure of the Pugliese cylinder. The unique defense system designed by General Umberto Pugliese failed to protect her from a single torpedo. Yet it was Pugliese himself, called back from exile, who engineered her salvation from the harbor floor. His underwater defense design was a theoretical error, but his salvage logistics were flawless. The operation to raise her remains a case study in the physics of recovery. It demonstrated that with enough buoyancy control and patience, even a 29,000-ton capital ship can be brought back from the dead. But it also proved a harder strategic truth. The salvage engineer can win the battle against the ocean, but he cannot win the race against time. The Conte di Cavour never fired her guns in anger again. She was a technical triumph that arrived too late to matter.